In our last installment in Chapter 9, in 9.6 that is, we're going to talk about circles and the Pythagorean theorem. So in this particular problem, we see that a tangent called AB is being drawn to the circle. And don't forget that a tangent to a circle is perpendicular to the radius at the point of intersection. So if our AB is tangent to circle C, remember it's named for the center, and you know that the AB is 6 times the square root of 3, we want to find the area of the shaded region. So how do we do that? Well, first of all, I know that if I'm going to figure this out, I need to figure out the radius of my circle. And what I notice right away is that I have a 30, 60, 90 triangle. From our rules before, we remember that to go from the medium side, which is across from the 60-degree angle, to the short side, which is across from the 30-degree angle, we divide by the square root of 3. Which means that I know that the radius CB is the same as 6, because 6 square root of 3 divided by the square root of 3 means that my square root of 3 is reduced, and that's how I get my 6 for the radius. Now that I know the radius of my circle, I know that the circumference, sorry, not the circumference, I mean the area of my circle is pi times the radius squared. Or in other words, I would have pi times 6 squared, which I would of course call 36 pi. But I don't want all of that. I look at my triangle inside of there and I see that the pi piece that was cut out, or in other words, this yellow highlighted part, is not going to be included in the shaded region. That's called a sector from our previous lessons. So somehow I can't include that sector. I want everything else that's shaded in the blue. Well, if that yellow pi piece takes out 60 degrees out of my circle, that means I still have 300 degrees in there. Or in other words, I have 300 degrees out of the 360, and this is my shaded degree measurement. So I take that proportion, or that ratio, and I multiply it by the area in order to find out what the shaded region was. So I see in the light blue that this proportion gets multiplied in the orange by the area of the circle to yield the light blue shaded area, which you could write down as 30 pi or 94.2. Either one would be acceptable. This is something we learned about earlier. The only caveat we have here is that we used special right triangles in order to help us figure this out. Again, that was when we went from the medium side of a 30, 60, 90 triangle to the short side of that 30, 60, 90 degree triangle by dividing by the square root of 3. Take a look. We are continuing to use things we've learned in the past to do things we are doing in the future. In our last slide, slide 2 here, what we're going to talk about is how do angles that are inscribed in a semicircle help us. So we learned earlier, much earlier in our class, that if you have an angle inscribed in a circle, it's half of the intercepted arc. For example, if I look at this red circle, whoopsie, that's not what I wanted, sorry. If I look at this red circle and I draw a central angle like this, and I tell you that that arc is 70 degrees, then this angle is 70 degrees. However, if I draw a different circle and I draw the inscribed angle and I tell you that arc is 70 degrees, the inscribed angle is 35. It's half. So that's something really important to remember. It's, again, something from our past. The thing for this particular slide is that when you look at angles that are inscribed in a semicircle, then you get a right angle. Why is that? That's because a semicircle is 180 degrees, and half of that would be 90 degrees. So the semicircle means half, or 180 out of the 360, and a right angle means 90 degrees. Surprise, surprise, something we already know. In this particular picture, off to the left here, if I were to tell you that in that picture, we know that AB was a 3, and we know that AD was a 4, from our Pythagorean theorem, and knowing that this is an inscribed angle that cuts off the diameter, which means that this whole arc going around from B to C to D has to be 180 degrees, we know that we have that right angle. I can use my Pythagorean theorem then and say 3 squared plus 4 squared equals BD squared. Or in other words, when I get done using my Pythagorean theorem, I find out that BD is 5. You can do the math later, but that's really what it's saying. But the real goal here is then to find the area. So once I know that my BD is 5, that's super important because now, since that's the diameter, I know that half of it is 2.5. Or in other words, if my diameter is equal to 5, my radius is equal to 2.5. So now if I want the area of this circle, I know that my area is equal to pi times the radius squared, which turns out to be, in the end, 19.625. So we used some ideas from the past, the fact that we had inscribed angles being half of the intercepted arc. We also noticed that if we intercept a diameter, that diameter cut off half of the circle, which meant that the intercepted arc was 180 degrees, which meant that the inscribed angle, therefore, was 90, or in other words, it showed us that we had a right triangle. That right triangle allowed us to find the length of the diameter. Finding the length of the diameter let us know what the radius was, because it was just half, and then we know the formula of the circle is pi times the radius squared, and then we can find that area. So putting together a lot of ideas in geometry to help us solve problems, all things from the past help us lead us into the future. Don't forget those things that we've learned in the past.